Let's see what lateral displacement is. This is the incident ray. It is moving from air into this glass slab. Thickness of the glass slab is what? T. Now we know that if this is air, this is some medium, and this is again air. That is, if this medium and this medium, they both are same, and these two interfaces are parallel, then incident ray and emergent ray, they both will make same angles. That is, if this angle is I, then this angle is also what? I. We had received this formula from mu sine theta mu m sine theta m constant. From this equation, we arrived at this conclusion that this angle and this angle, they are same if this medium and this medium, they are same, provided these two surfaces are parallel. Now, our aim is to find lateral displacement. What is lateral displacement? This is the incident ray. If you remove the glass slab, then its path is shown by the broken lines like this. But because of the presence of glass slab, now you can see what it deviates, and then it further deviates, becoming parallel to what? The incident ray. Separation between these two is called lateral displacement. Our aim is to find this much separation. Let's call it x. This x is the lateral displacement, and we need to find x in terms of I, R, and refractive index of glass with respect to air, which is, in this case, mu represents refractive index of glass with respect to air. In a general situation, it can represent refractive index of medium 2 with respect to medium 1. If you say that this is medium 1 and this is medium 2, then this is again what? Medium 1. In that case, this mu will represent what? Refractive index of second medium with respect to first medium. In here, it's simply what? Refractive index of glass with respect to air. Now, at this stage, you should pause the video and go for x. It's not difficult. You need to simply use what? Geometrical concepts, and you can find it. Now, let's see how we calculate this x. If this angle is I, then this is also what? I. Opposite angles. This is I, this is R. That means this much is I minus R. This is I minus R. This is I. This is R, and therefore remaining is what? I minus R. And this is I minus R. This is X. This much is also what? X. From this point onwards, you can see that they both are what? Again parallel. Before this, they are not. After this, both these are what? Parallel, and therefore this is X, this is also what? X. Let's call it A, B. Our aim is to find AB. This AB is what? X. This is AB. Let's say this is C. Now you can see a right angle triangle. This is the right angle triangle ABC. In this right angle triangle, we need perpendicular. We have the angle I minus R. If we can find out this AC, we can easily calculate AB. Look here. AB upon AC. AB upon AC is what? Sine of I minus R. We just need what now? AC. It is also very clear. If you join this normal, at this point, let's call it D. If this point is D, then CD is known. That is what thickness of the glass slab. CD is known, R is known. This R is known, and therefore, in triangle CDA, in triangle CDA, you can see that this is R, CD is the base, and CA is the hypotenuse, and therefore cos of R is simply CD upon CA. CD upon CA. CD is already known. CA is something we are interested in. We need CA. And we have found it. CA is coming T upon cos R. That gives us lateral displacement AB, which is X as AC multiplied by sine of I minus R, where AC is T upon cos R. AC is T upon cos R sine of I minus R. This is the lateral displacement. They simply ask a 2 marks question. Find out lateral displacement. There is nothing much. It's a simple geometrical concept. Very easy. Good for scoring. Note down this. Now let's see total internal reflection, TIR. We know that if light moves from a denser medium into a rarer medium, when it moves from a denser into a rarer medium, it moves away from the normal. This is the incident ray, and that's your normal. Then it deviates like this, away from the normal. This is I. this is R. Let's say refractive index of this denser medium is mu. If I say that refractive index of denser medium is mu, then it means refractive index of denser medium with respect to rarer medium, that is given as what? Mu. Now, if you write sine I upon sine R, and sine I upon sine R, you simply write mu. Mu, which is refractive index of denser with respect to rarer, then I hope you know that it's not correct. Why it's not correct? Because sine I upon sine R, sine I upon sine R means what? Refractive index of this medium with respect to this medium. Refractive index of the medium in which light enters with respect to that medium from which it is coming. And this is, 1 upon refractive index of denser medium with respect to rarer medium, which for us in this article is simply 1 upon mu. And therefore remember, when you write sine A upon sine R, if you write mu, which is this mu, then it's not correct. It should be 1 upon mu. Now, once you say that R is greater than I, it moves away from the normal, then if I increase this angle of incidence, look at the structure of this whole ray diagram. It's something like this. This is I, incident ray, and this is your refracted ray. If you increase the angle of incidence, then angle of refraction will also increase. At one point, refracted ray becomes parallel to the interface. Something like this. At one point, your refracted ray is parallel to the interface. This, if you say, is a critical angle, let's call it I naught. This is the critical angle I naught. For this critical angle I naught, this critical angle R naught simply becomes what? 90. When angle of incidence is I naught, angle of refraction is R naught, which is 90. After this, if you further increase the angle of incidence, light will move into this medium. In which medium? In the denser medium itself. It's coming from denser, it's ultimately moving into what? A denser medium. That means now there is no refraction. It's what? Simply reflection, and therefore we call it what? Internal reflection. Total internal reflection means if you have I which is greater than I naught, then all the rays, they will simply move back into the same denser medium from which they are arriving. That means if you have a ray like this, if you have an incident ray like this, it will suffer no refraction. Instead, it goes like this. and becomes what? A reflected ray. This I is greater than I naught. For the I greater than I naught, your reflected ray will also make what? Same angle. Concept of reflection. Angle of incidence is same as angle of reflection. Now, aim is to find I naught, which is not a difficult thing. You can see it from here. But remember the concept. Total internal reflection. Now, in normal situation, what happens? In normal situation, part of the incident rays, they get refracted, they come out, and a fraction of that energy which is coming gets reflected. That is called partial refraction and partial internal reflection. It happens all the time, all the angles. But once you cross this threshold, this I naught, then no part of light or energy can move from denser into rarer medium. All that energy will be reflected back into the same medium, and therefore we call it what? Total internal reflection. Our aim is to find this critical angle I naught. Let's find it from the help of this formula which we have got, sin I upon sin R. Now, sin I naught upon sin R naught is what? 1 upon mu, but R naught is what? 90, and therefore sin 90 simply becomes what? 1. This is 1, which is 1 upon mu. This gives us I naught as sin inverse 1 upon mu. That's the critical angle of incidence, after which all the rays, they simply move back into the same medium. The important thing is what? For TIR to take place, light should always move from denser into rarer medium. Write down this as a statement. For total internal reflection to take place, light rays should always move from denser medium into rarer medium. From denser medium into rarer medium. Now, the way they can ask you a question on this, they have given you that for water and glass, for water and glass interface, find out critical angle. Now, if they ask you something like this, then critical angle I naught is what? Sin inverse 1 upon mu. But which mu? For that, remember this. What is mu? Refractive index of denser with respect to rarer. This mu is of denser with respect to rarer. Now, a much better way is the next one. This thing we know is nothing but refractive index of denser medium divided by refractive index of rarer medium with respect to air, which means this part simply becomes sin inverse mu rarer upon mu denser. This is 1 upon. 1 upon of this will give you what? Mu r upon mu d. It can never be mu d upon mu r. It's a very easy thing to remember. It's always rarer upon denser. Why? Had it been mu denser upon mu rarer, then inside the bracket things are greater than 1. But you can never have sign greater than 1. And therefore, from now on, it's better to remember critical angle like this. Refractive index of rarer divided by refractive index of denser. Much better than this presentation. Now, if you have water in glass, then you know which one is rarer and which one is denser, and therefore this is coming sine inverse rarer is water and denser is what? Glass, which is sine inverse refractive index of water with respect to air is 4 by 3. That of glass with respect to air is 3 by 2. This gives us sine inverse 8 by 9. 2 into 4, 3 multiplied by 3, that is giving you sine inverse 8 by 9. Suppose you use mu denser upon mu rarer. If you write mu denser upon mu rarer, it will look like 9 upon 8, which is greater than 1, something which is not possible because sine can never exceed 1. So from now on, remember critical angle like this, sine inverse mu r upon mu d. And the thing which I told you, reflection and refraction, they always take place, but when you move light rays from denser into rarer, and for angle of incidence greater than I naught. At I naught, light is at the grazing angle, just touching the interface, but beyond this I naught, all the light, it simply moves back into this part, and therefore it's called what? Total internal reflection. Note down this, and then we'll see a question based on it. Look at this question based on total internal reflection. Let's say we have a lake and at the bottom of the lake we have a light source. Let's say a bulb is there, light bulb, and depth of this lake is 10 meters. Now, somebody looking at this light source from outside, from air, this is water. Somebody looking from outside at the light source, he will find that light rays are coming straight like this, then they come like this in all directions, but beyond a point, because of TIR, no light rays can enter into air from water, and therefore somebody looking from outside will find that you have a circular patch or circular bright spot at the surface of the lake from which only light rays are coming out. Question is, we need to find area of that circle. Write down the question. A light source is at a depth of 10 meters inside a lake. Find out area of the lake, find out area of the lake surface from which light rays are coming out. find out area of the lake surface from which light rays are coming out. Again, it's a very easy question, simple geometry, and you can answer this thing. Pause the video, go for it. Now what happens? This ray, which makes an angle of I naught with the normal, and that's the normal. If this is I naught, this is also I naught. That's I naught. Then this ray simply moves like this at grazing angle. This is R naught, which is 90 degrees. That's your incident ray. Any other ray which falls on this side will be simply reflected back into what? Lake. And therefore we are not interested in that. And I hope you can see this distance, if is R, then our aim is to find area which is nothing but pi r square. A light ray which arrives at an angle of I naught, moves at grazing angle, all the light rays coming after that will be simply reflected back, and therefore you will find a cone sort of. You will see a cone, and we are interested in finding base of the cone, and that base of the cone is a circular portion, a circular bright spot whose area is what? Pi r square. The question is simply find r and then go for pi r square. Now how do you find this r and all? For that, first let's use the information from critical angle. Sine of I naught is what? 1 upon mu, which is refractive index of water with respect to air. We know that this is 1 upon 4 by 3, and is coming 3 by 4. We have the information of sine I naught. Now it will help us. Look at this triangle. This much is r, and this angle is I naught, and this height is given as what? 10, and therefore tan of I naught is perpendicular upon base. Tan I naught is perpendicular, which is r, upon base, which is 10. R upon 10. But we have the information of sine. How do you find tan? Not a difficult task. Just construct right angle triangle. Say this angle is I naught. Then if this is 3, then this is 4. What is sine theta? P upon h, perpendicular upon hypotenuse, and therefore this is 3 upon 4. If this is 4 and this is 3, base is what? 4 square minus 3 square. 4 square minus 3 square, which is coming 16 minus 9, root 7. Now what is tan of I naught? Tan of I naught in this triangle is what? 3 divided by root 7. 3 divided by root 7. That gives you r as 30 divided by root 7. We got the answer, which is pi r square. Pi multiplied by 30 upon root 7 square. That's the area from which light rays are coming out. A simple question based on total internal reflection. Note down this.